Okay, first of all, rational functions. It's p of x over q of x. It's zero if p of x is zero. And q of x ain't. Okay. This is a fundamental thing you got to know. There's a little more you could say about this. You got a vertical asymptote. If q of x equals zero and p of x ain't. Okay, you got to use formal mathematical language. Ain't. Okay. And there's more. Those are the most basic things other than the long run behavior, which we'll talk about in a little more detail. Okay. I mean, the long run behavior is pretty straightforward. I just don't have room to write it out. We're going to be reviewing this in class where I'll talk more about it. Okay. But that's really kind of the beginning of what you have to understand. The other part is, if the degree of p of x is bigger than the degree of q of x, it goes to infinity or minus infinity in long run. If they're equal, you have a horizontal asymptote. And if the degree of q of x is bigger than the degree of p of x, you have a horizontal asymptote at the x-axis. Those several things. Just given I didn't leave a lot of room there. That's what we're going to talk about today. Unless we find that we have more time, we can come back and talk more about it. Again, we'll address it more in the precalculus class. Okay. Exponential functions. Okay. I think everybody started off with a graph. Okay. And the way I've emphasized graphs in this course, that's natural. There's also a basic form for the exponential function. Okay. So the basic exponential function is y equals 2 to the x, which I think you're pretty much on top of, because at least one of you made a table and a graph, and both of you made graphs. Okay, if you make the table, you're more likely to get the graph right. So we have our table. Now I'm just indicating the table. You know how to make the table. Okay. And if you make the table, you get the graph. I'm drawing it small because I've been drawing it big for a long time, and I'm getting hard. No, it's a graph that I'm sure everybody here is right on top of. Partly because at least one of you made the table of the graph, and both of you made the graph. Okay, so everybody knows how to line off the graph and plot the points. They have points like this. And there it is. That part should have been higher or the left. Anyway, didn't quite get it right. You don't have to get it completely right either. Okay. And we want the graph to be equally scaled, at least have a uniform scale on the x-axis and a uniform scale on the y-axis. Okay, so there it is. Now this graph can represent any exponential function, provided you don't have a negative exponent, because you can also have a negative exponent in a general exponential function. Okay, so okay, there we go. So can I get a little further along before I write something down carelessly? Try to focus my attention a little better. Okay. Y equals a b to the x. Or y equals a times 2 to the kx. Or y equals a times e to the kx. This form is the form you want it in if you're going to do calculus with it. So if you have an applied calculus in your future, or a full-blown calculus in your future, and who knows? Okay. You don't want to do calculus in this form or this form, although you can. It isn't that hard. I'm not going to say any more about that, except that the derivative, which is the rate of change, has a particularly simple form when it's in. If you have the exponential form in this form, the derivative is just going to be k times a e to the kx. Now the derivative tells you rate of change at any point, tells you how fast the things change. If you do this one or this one, you're going to have a log of 2 times k a times 2 to the kx. Here, you're going to have a log of b involved, which just complicates things a little bit. Particularly simple here because you don't have a log expression in the rate of change function. So you don't need to know that. Just whetting your appetite, try to stimulate your already incredible interest and motivate you to tackle a calculus course at some point if that's in your best interest. Okay. I won't tell you not to be afraid of it, because if you're not afraid of calculus when you start, you're not going to work as hard. But don't be terrified of it, because you can do it. Okay. You always want to be a little afraid when you go into a challenging course, just enough to motivate. Okay. Let's see. So those are general forms. In terms of a b to the x, graph looks like this. If b is greater than 0, and like this, if b is less than, there's another mistake, greater than 1 or less than 1. If b is less than 0, not even defined, because you can't define the exponent in general for negative number. simple example is if x is 1/2, you can't do a negative number to the 1/2 power. And since you want to actually take any value, there are plenty of values, not just the 1/2 power, which is a square root, but infinite number of values on any interval of the real line, no matter how small, which is kind of another really neat idea that you don't need to worry about. Okay, so that's as much as I have room to say about exponential functions. Of course, there's a whole lot more. Okay, logarithmic functions. Your basic logarithmic functions inverse to your basic exponential function, which means you have a table for the exponential function. And a table for the log function, where you switch columns. You understand how that diagram indicates that you switch the columns? This arrow points to this column, and this end of the arrow points to this column. So the right-hand column of this one is the left-hand column of this one. So I could have written switch columns, but I wanted to indicate the tables and indicate it graphically. And I don't want to take up the root because I'm doing this one short. And just trying to do a short synopsis of the most important ideas. Okay. I think I know how to walk. Okay. So your graph then inverts the graph of your basic exponential function. Meaning your -2 to 2 would go here, and your 0 to 4 would go here, which would put 1 here. Okay. The inverse to the point 0, 1 here is the point 1, 0. That's going to be a point that you really want to focus on. And inverse to the point 1, 2 on your basic exponential function is the point 2, 1. Here's 2, here's 1, so here's the point 2, 1. And inverse to the point 2, 4 is the point 4, 2. Now I'm going to have to do just a little repair because I put my 1 too far over. Should have subdivided that interval. I had a chance to do it without embarrassing myself. Okay, so anyhow, there's 2, there's 4. And of course, that gives you this point. And then x equals 1/2 and 1/4. You take the points -2, 1/4, and you get the point 1/4, -2. Take the point down here, -1, 1/2, and you get the point 1/2, -1. Well, it's going to be about here. And now you have a graph that's a little more nicely shaped than what I just drew, but you get the idea. And you can draw good graphs. Okay, the graph of the logarithmic function has to go through the inverse of each of the points of your basic log function. Okay, now, let's go back to the basic log function. In the form y equals a times 2 to the kx, you have the basic exponential function, but you vertically stretch it by factor a, and x has been replaced by kx, so you horizontally compress it by factor k. Now, usually k is going to be a small number, so it actually expands it in this direction. So you want to understand that. It's visual, it's fairly easy. We'll talk more about that in Precalculus class, but that's your fundamental idea. And our goal here is to give you kind of an overview and a synopsis. Hopefully, all the work you've been doing, and you've been doing a lot of work, as has everybody in the class, which is really wonderful. Let's try to make the pieces of the puzzle fit together a little bit. It makes it much easier to prepare for an exam. Okay. Okay, exponential logarithmic equations. First of all, your fundamental thing, and it's the inverse function relationship. Basic thing you need to know is that I want to write E because we do want to be able to do this with E, but not right now. B to the A equals C. Is equivalent by the fact that log base B is inverse to B to the X, okay? So the exponential function base B. Equivalent to log base B of C equals A. And you want to try to remember that. Because I'm not going to give you that in a formula sheet or anything. It's something that you've used a lot. You want to be prepared to the extent that you don't need somebody to tell you that. Okay. That's not all you need to know. That's all you need to know. That and how to do basic simple algebra of multiplying both sides of the equation by quantity, adding same quantity or subtracting on both sides, okay? And the goal here is to use this if the exponent involves your unknown, okay? You use this. You know, maybe I ought to reverse this. Oh, no, don't break. The ones that listen to me. Okay, let me do this a little differently. I'm going to use some arrows. The idea is fairly simple. you convert from this form to this form. If the unknowns in your exponent. Because if, like, you're solving for x and x is here in the exponent of b, you can't get to it except by converting to this form, in which case your exponent, which is in a, is now down here, where you can use adding, subtracting both sides, and all the techniques you know about how to solve algebraic equations, okay? You use this if your unknown is inside the log. It's probably written too small for you to read. Hopefully, cameras got good resolution so you can read it on camera. That's what it says. And it's something you know. At least you knew it when you did the assignment, because everybody did real well on those assignments. Okay, so it's really not particularly difficult to solve exponential logarithmic equations if you know this and know which way to go. If you have if your exponents in the log equation, if your unknowns in the log equation, you convert it here, and then your exponents not wrapped up inside the log anymore. If your unknown is in the exponent, then you switch here so that your unknown is no longer wrapped up in the exponent. You can get to it and you can do things with it. Now you might have some horrible expression here for a clinic equation or something like that, but nobody's going to ask you to do that in this course. And we'll see how this expands into a variety of examples as we move on, mostly in the precalculus class. Okay. The other thing I wanted to say about this is, the other thing you really need to know is log base b of a is log a over log b. And of course, you might need to use properties of logs, which gave nobody any serious trouble. That word is log, and I can't make that G any better without risking total disaster. Okay, people did quite well with properties of logs when they had them in front of them. Okay, and a lot of people did just fine when they came into class and didn't have the properties of logs sitting there in front of them. So I don't think it's anything that's going to give you serious difficulty, provided you have time to review sufficiently and do it in an efficient manner. Okay, now, a couple of things about the graphs. Your graph of your basic logarithmic function. And let's do the inverse, not the inverse, the reflection. this would be like b raised to positive multiple of x. This would be like b raised to negative multiple of x. And you should know that. We'll talk more about it. This can be labeled represent any log function in one of the general forms that I've written down here. Now you can always vertically stretch. I mean, vertically, you've got a vertical stretch factor in any case. And you've also got a horizontal compression factor, which you can see most easily in this form. In precalculus class, we'll talk about how these forms can be converted into one another. Then I think I didn't complete my sentence. That's good. Okay. If you draw your basic logarithmic function, you can relabel it to represent any log base b function. Okay. In other words, every exponential function that has an asymptote, horizontal asymptote at the x-axis can be labeled, can be represented by labeling one of these graphs, depending whether your exponent is positive or negative. Your basic log function graph, and you should recognize this as your basic log function graph, can be labeled to represent any log base b function. Okay, we'll talk about it for calculus class. We might well have time to talk about it in here. I'm doing all the talking today. I'm not asking you to do anything except absorb these nuggets of incredible wisdom. Okay, start putting the pieces together for your own benefit. Okay, so I'm going to leave it. I'm going to leave it at that. I was going to kind of almost forgot what I was going to say. If this is a log base b of x, then this point is always going to be 1, 0, because on any basic exponential function, on any b to the x function, 1, 0, 0, 1 is a point, so that 1, 0 is. Okay, b to the x is always equal to 1 if x is equal to 0, because 0 power of any number is 1. Because of that, you have the point 0, 1 here. You have the point 1, 0 in the inverse function. And you also have then the point 1b. So I'm going to have to do that. I've left myself a little more space when we get a little deeper into the analysis. But here's a guideline for an analysis of pretty much everything that we've done since rational functions, except for the matrix stuff. And we'll talk about that too. We'll talk about that in a minute. Okay, give you a chance to copy down whatever you want, process that for a short time, and then we will do a summary of what we need to know about systems of equations, systems of linear equations, and elimination and use of matrices. Okay, as I said, I started to dive into systems of linear equations. What I really want to do is similar to what I did here. List maybe 4 things, maybe more, and ask you to write down what you want to write down, what comes to mind. Okay, give you 5 minutes on that, 10 minutes if you're still writing, less if you're all broken your pencils and are beating your heads in the desk or something. Okay, we don't want to drive you to frustration on this. So we'll just judge how long you need to get your head into the situation. Okay. Okay, now y'all are still writing and still writing good stuff, and I really like that. It's great to see. But you know, my job is to stand up here and talk, right? Actually, ideally, my job is to simply pose problems, watch you solve them, and not have to say anything, just stay out of your way. Okay. But that's a bit of a stretch in this course. But some of you are closer to that than you think you are. Okay. So anyhow, systems of linear equations. I already wrote solve by elimination, because that's what we really want to do with linear equations. Now, some of you wrote substitution, and I did say, if I ask you to do the problem by elimination, you better know what that means and do it by elimination. If you solve it by substitution, I might give you a few points. Okay. Now, if I don't specify the method and you want to use substitution, have at it. It's fine. The reason we stress elimination is substitution ain't going to work when you get down to reducing augmented matrices and doing matrix equations, stuff like that. Okay. So I solve by elimination. And what does it mean to solve by elimination? You multiply an equation by a number. I should have left myself more room to write that out. Okay. Or you can add multiples of 2 equations. That's basically it. Except for the obvious thing, you can change the order of the equations. And I just say, write the equations in a more convenient order. If you want the 3rd equation to be the first, just because it lines things up for you more nicely, that's totally acceptable. Obviously, the solutions to the equations don't depend on the order in which the equations are written. I've said, for example, for a system of 2 equations and 2 unknowns, that's equivalent to 2 lines on a graph. Doesn't matter in which order you plot those lines, they're going to be the same lines and they're going to have the same intersection point if they do intersect. Okay, now we'll talk about the cases where they don't intersect. If they're parallel, they might be parallel and not intersect, but they could also be the same equation, in which case they're both parallel and intersecting. So it's kind of important to understand those things, but right there are the basics. Elimination, there are three things you can do. Change the order of the equations, multiply an equation by a number, or add multiples of two equations. Multiply one equation by a number, multiply another equation by a different number, add them up, preferably to eliminate a variable. Okay. Now, how do we represent by matrices? Let's take the square brackets. Okay. That represents an augmented matrix. Now there's a row here, a single column of numbers here because this stands for the left-hand side of each equation. Each row will represent the left-hand side of one of the equations. And here we have the right-hand side. So each row of the entire matrix represents one equation. And this kind of is representation of the equal sign. And you want to keep that in there so you don't lose track of what you're doing with the matrix. We don't multiply augmented matrices by anything. We simply reduce them. Okay. So this is an augmented matrix. This is the matrix equation. Multiply matrix by column. Okay. In the column is like I wrote X, Y, Z, W. You can have as many equations as you might wish. Okay, there's all kinds of important applications that involve thousands, even millions of equations. And you run out of letters pretty quick and you use subscript variables. You don't have to worry about that. So, a matrix equation. Either of these can represent a system. You have to know how to represent a system both ways. One reason you would use the matrix equation, and we're not going to get into how to invert a matrix. If we had a day, I could show you. It's not that hard. It's just tedious and error prone. Okay. But you could write a matrix equation in the solution to the matrix equation in any computer algebra system. The solution to the matrix equation is writing these letters really tiny. I'm not sure that they can show up, especially that one, but X, Y, Z, W equals the inverse of this matrix times this. Now, those are details. I'm not going to define it. I don't have room to write out the definition. Just this is the inverse of this matrix. It's like you multiply both sides by the inverse of this matrix. When you multiply the inverse of the matrix by the matrix, you get what's called the identity matrix. And that just leaves you X, Y, Z, W. The same way that multiplying 3x equals 5 by 1/3 leaves you x equals, okay? And then, of course, this is the matrix that you have here. Because when you multiply the inverse by both sides, this is what you get on the other side. Well, we did that. We haven't talked a lot about it since we did it. Simply because we got hung up in the details of elimination, matrix reduction, how to reduce an augmented matrix. Okay, that took us a good day longer than I expected. But I encountered the same thing in the linear algebra class. I still don't know why that isn't as clear as it could be, but obviously it isn't. And I actually remember when I took linear algebra, I had to think about it a little bit. Okay. So it wasn't totally obvious. Partly because it's being explained by somebody who didn't speak English. Okay. It's pretty interesting. You know, the degree of a polynomial. Okay. The degree of a matrix, the degree of the system equation, the degree is really important. I was 2/3 of the way through the course when I understood what he meant when he said diggity. There's a song, hot diggity, dog diggity, boom, what you do to me. Okay. So every time he said that, I said, I know he's not talking about that song, but what in the world is this guy saying? He also talked really fast. And you know, with a strong, some kind of a Middle Eastern accent, maybe Pakistani, maybe Indian, I don't know. Maybe anything. Okay. Of course, I didn't have any professors that semester who were native English speakers. But my ear adapted real well to what I have. Indian. So this guy wasn't Indian, but I had an Indian professor, a Chinese professor, and what was it? I think French. Okay. I could understand them all except this one guy because he was talking so fast. And I didn't realize at the time that even at that time, I had some hearing loss. Wasn't too bad at the time. Okay, anyhow, here we are. So if I happen to slip and talk about the dignity of an equation, you'll know what I'm talking about the rest of the class. Okay, reduce an augmented matrix and interpret. How do you reduce an augmented matrix? You can switch rows for convenience. Like if you got a 1 in the first position, you know, it's down here, it's usually convenient to put that row on top. It's equivalent. What you do here is totally equivalent to what you do with systems, except you've got to do it in a little more organized manner when you have an augmented matrix. Okay. Multiply a row by a non-zero number, and I should have used non-zero. I can't written small enough because it's hard to be able to read it from the but obviously, if you multiply an equation by a zero number, you change its solution. You don't get any information out of 0 equals 0. And You might have more than 3 rows. You're not going to in this course. If you do it for 3 rows, you're good. Okay, because you can do it for 3 rows, you can do it for 50. You just don't want to do it for 50 because it takes a long time. And there are actually other forms that this could end up in, and we're not going to go deeply into those. Just kind of trying to get the basics. Okay. Now multiply matrices. First thing you have to understand is what it means to multiply a row by a column. Okay. And then if you have about another time. And I might not get to this general problem. I'll get to it in the next hour. Okay. Row times a column gives you a number. Here. You have multiple rows. So you have a row, a row, a row, row. Okay. You might have a bunch of rows here. Now, practically, you're only probably going to see 3, although I could easily ask you to do one with more than 3 rows, just to make sure you understand the principle. You multiply each row by the column. Each row by this column gives you a number. You get a number for each column. And I should write out, you get a number for each column, but I didn't make myself room. And 200 hours come. So I'm going to actually stop on time, since we're going to get to go on with it. The class. We have a framework for what we're going to do in the pre-calculus class, which is going to be have everybody expand on what I've written up here. Okay. See if you can think of examples, stuff like that. And I just want to see how the class does. We'll adapt as we go along. And then we'll fill in more details. Clock just changed. 12:30. Right here's the course. You got it? Okay. Any questions? Well, okay. We're going to go over this. We did this in the last class, and I'm doing the last class and this class in the same video. Okay, since we talked about this in more detail during the last class, you can have reference to that. I'm going to make a funny comment and decide it wasn't funny. So I'm not going to make it. Okay. Here are some of the main topics of the course since the midterm. everybody did pretty well in the midterm. Everybody passed it. Some people like to make a higher grade. Most people did just fine. Okay. Now, one thing that was in the midterm is our friend the rational functions. So I'm going to go over all this kind of quickly, and then we're going to start filling in details. I'm going to ask you to fill in details by showing me examples. I want to see if you can write an example of each of these things. Okay. And when I say you can't write an example, then I'll do it for you. Okay. And I'll do it for everybody. I want to gauge what people are good at, what they know well, what they remember, because it's been a few weeks since we've done some of this, and what you need a little more information on. Now, again, we have this week and today and 2 classes next week to do a really pretty thorough review. And hopefully that's going to get everybody over the hump, and everybody whose grade can still be raised. That wouldn't be everybody. And everybody maybe even raise their grade higher. Okay. It'll be challenging. Make sure it doesn't go the other way. Rational functions. A rational function has a form y equals p of x over q of x. It's a polynomial divided by a polynomial. Y is going to be 0. In other words, the function is 0 if your numerator is 0, because that's what makes a fraction 0. Fraction 0 if the numerator is 0. If the denominator is 0, now remember that exercise we did early in the course, where I said, okay, you go twice as close to the x-axis, you go twice as high. Go twice as close, you go twice that high. You go twice as close as that. Well, I don't want to jump because I don't want you to see my feet on the screen here. Okay? Because my shoes are a little scuffed and that'd be embarrassing. Okay. As you get closer and closer to the y-axis, x gets closer and closer to 0. And y gets bigger and twice as bigger and twice as bigger than that. In 10 steps, it's 1,000 times bigger. In 20 steps, it's over 1,000,000 times bigger. In 30 steps, it's over 1,000,000,000 times bigger. It doesn't take too much longer before you get from here out to that spacecraft that's orbiting the moon right now. Okay? And that's a long ways away. If you had a road where you could drive to it, it would take you 4,000 miles, 4,000 hours. And 4,000 hours, that's 40 hours a week for 2 years. That's how far away the moon is. But we could get there by letting q of x be small enough. Okay. Meaning that you get a vertical asymptote as q of x approaches 0. So you have a vertical asymptote if q of x equals 0. Now there's more to it. I say there's a little qualification here. If p of x is 0 and q of x ain't. Okay, because if p of x is 0 and q of x is 0, it's a little more complicated. Talk about that, but not today. A vertical asymptote if q of x is 0 and p of x ain't, because if both p and q are 0. Well, again, we'll talk about it. It's not hard to understand. You've seen it, but we're not going to worry about it right now. We're trying to get the most basic idea down. Fair enough? Okay. Exponential functions. Well, I asked people in the last class, I just threw out these words, and these words, and asked people right now. Okay. And what I saw immediately was pretty much everybody drew a graph. Okay. Preferably made a table to make sure the graph is right. Because that's how you get the graph. You don't just remember, it goes kind of like this. Okay. Put it in the wrong place. Vertically shift it, flip it around, Okay, well, you can do those transformations. And you pretty much know how to do that. And you want to be good with transformations when you get to the exam. So right now, looking at the most basic thing. You have your basic exponential function, which is y equals 2 to the x. You make a table and a graph, and everybody can do that. You do have to show details of how to calculate the table because I want to know that you know what these numbers are doing, so you know why the graph has the shape it does as deeply as possible, because that just goes back to basic arithmetic. And if you don't build your understanding here on basic arithmetic, it's kind of like the old castle builder and sand thing. Okay, it doesn't sustain itself. It's shaky. Okay, so anyhow, this function, of course, can be modified in the most straightforward way by giving a vertical stretch by factor A and a horizontal compression by factor K, or horizontal expansion if K happens to be less than 0. So that means this graph can be stretched this way, and or it can be compressed or stretched this way. And A and K govern how that happens. You should understand transformations completely. Yeah, you did some really good work with transformations. We didn't talk a lot about the compression, but you're in a position to understand that, horizontal compression. Okay. Other forms are A equals B to the X, which is pretty well taken as another really standard form. I relate it to the 2 to the X function as 2 to the X function is really easy to understand. And of course, your open math materials and most textbooks regard this as your basic toolkit function for an exponential. And I'll even give you a little preview. B is just 2 to the K. So if you know B, you can solve the equation 2 to the K equals B and switch from exponential to logarithmic form. Okay. So it's really easy to relate this to this. All right, it's fairly easy to relate to this form. The A equal AE to the KX. Okay, AE to the KX. Why do you use E? It's because in a calculus course, some of you have calculus courses, at least an applied calculus course, you learn it much better if you understand what the heck is going on, which is why we're doing this course. Okay, you have a rate of change. Now, rate of change is one of those fundamental concepts. We're not even going to talk about it today, but we will come back and talk about it. But the rate of change is just the slope of your graph. Slope of your graph at a point is just the slope of a tangent line, a line that just brushes the graph without going through it. Okay? It has to have a certain specific slope before it can do that. And that slope is the rate of change. It's how fast the exponential function is changing at that instant. At the next instant, if it's an exponential function with a positive b or positive value of k, then it's increasing. And every instant it increases faster than it did in the last instant. You want to, this is a pre-calculus course. So I'm talking a little bit about how this is related to calculus. And if you think you even have a remote chance of needing to take a calculus course, you're tuning in on this, it gives you a head start. Okay. And if you got a real good chance, you really ought to pay attention. But I'm not going to talk about it much. I'm just going to tell you that there's an easy way to calculate the rate of change here. I'll even tell you what it is. It's k times a e to the kx. So if your exponential function is of the form a e to the kx, you just multiply that by k and it gives you the rate of change right now. If you've got money in an account at a certain interest rate that's been compounded continuously, if you know how much you got right now, and you know the interest rate, you'll figure out exactly at this instant. Of course, if you figure it out for this instant, it's going to be a later instant because it takes a while to figure it out. Yeah, that doesn't change that much. Okay, so you can calculate it and figure out how many dollars for you're earning at this instant. And then if you want to feel good, calculate it an hour later and say, hey, I'm making money faster. Okay. Yeah, well, there are lots of examples. If you want to calculate that rate here or here, well, in this case, there's a log of K involved in calculating the rate. In this case, there's a log of B involved in calculating the rate. Okay. And it's just a little more complicated. So the reason we do the e to the kx thing is because that's what's easy to do calculus with. If you see this in a calculus course or this in a calculus course, you're going to say, boy, I wish it was this. But you already know how to convert from this form into this form, so it could be. Okay? Either that or you learn another rule. And you actually probably want to be able to do both. Well, people always wonder why the E thing, why the natural log and stuff. Okay. And that's the basic reason. It's the easiest base to use if you're doing calculus. Okay, so I'm not a calculus now. Obviously, you know how to do the graph. Or if you have the form a b to the x, if b is greater than 1, you have this. If b is less than 1, you have this. Okay. And we could also throw in 2 to the negative kx, which is just, or 2 to the negative x. So here's a graph of 2 to the x. Here's a graph of 2 to the negative x. And of course, you understand that by replacing x by negative x, that just reflects everything to the other side of the y-axis because you know transformations. And maybe not, because it's been a while since you really talked about it and had to use it. It's something you're going to want to review because it's really fundamental. Again, there are a lot of things that are hard to understand in calculus course. They're a lot easier to understand just through transformations. Okay, like for example, if I transform this by adding a number 2 to the x plus 8, okay, does that change the slope for given x? Well, it doesn't change the shape of the graph. You just go up a higher point and you still have the same slope and the same vertical line. Now, there's a lot of machinery in calculus that proves that. If you're not taking a full-blown calculus course, you're probably going to do a lot of proofs. Still, whether you prove it or not, whether you use this thing to prove anything, it makes a certain rule in calculus really easy to understand. Okay, and that's true of most of the rules used in calculus. They're easy to understand if you understand how they relate to transformations. So kind of emphasize transformations. Okay. Logarithmic functions. What's this picture tell you? Tells you to do an exponential function and you reverse the columns. This column becomes this one, and this column becomes this one, right? So I'm just saying, reverse the columns of an exponential function. I assume you know that. I assume you know how to do an inverse of any function by using the table and sketching the corresponding graph. Okay? And we'll talk more about that when we go back to the early ideas in the course, like what do you do if you do an inverse of a quadratic function, which has a parabolic graph. You get a graph that doesn't obey the vertical line test anymore, and you got to choose a branch. Just try to jog your memory. I'm not going to talk about that today. We'll talk about that next week. We got ample time to do a nice review. Okay, exponential logarithmic equations. What do you need to know about exponential logarithmic equations? B to the A equals C is equivalent to log base B of C equals A. Also, log base B of A is log of A over log B. And keep my notation consistent with what I have here. We're going to probably ought to, instead of log A, do the log of C, because that's what I have above. So let's just say this is true for C as it is for A, but if we started with an exponential equation and converted it to logarithmic form, then we're going to have log base B of C, so it makes sense to write use C instead of A. Okay. Now, when do you do this? You convert from this form to this form if your unknown is here. Because here is the exponent and your unknown is bound up in the exponent and you can't get to it to solve for it. Okay? You put it in this form and the exponent becomes just another set of terms in your equation. And you can, if you can solve, if your exponent's a reasonable expression, you can solve the equation. Now, if your exponent's unreasonable, you're still stuck. In that case, you kind of go to your graph. And you just do a graphical solution. I've done a lot with graphs and estimating things. So you should understand how you can use a graph to estimate a solution. I'll talk more about that. But yes, what did I ask you to do? One of the things I asked you to do was, okay, solve the equation 2 to the x equals 3. How do you solve that with the graph? You go up to 1, 2, 3. You go over here and you find out what x has to be, right? Or if you want to find out what 2 to the 1/2 is, and don't have your calculator handy, you got a good graph, you can pretty well do an estimate. You go to 1/2 and over, you find spelling that. Okay? If you got a good graph, get an estimate. And you can draw a graph good enough, well enough. You draw it big and draw it carefully and take a little care with your scale. You'll come out with an estimate if your projection lines are straight and all that. Okay. Now you also have the properties of logs, and I didn't leave myself a whole lot of room here because when I wrote this stuff out, I wanted to confine it to the most basic things that you kind of need to know. Okay, the properties of logs, like the log of AB is log of A plus the log of B, or the log of A to the C equals C times the log of A. Those are the basic ones. Y'all did real well with that, so I chose not to write those rules out, but when we expand on this, we will. But you should know what they are. Now, in a little while, I'm going to shut up and I'm going to let you ponder this and see if you come up with examples or flesh some of this stuff out. Okay, just what can you do with this outline here? That'll show me what you can do with the outline, which in some cases will be quite a bit, in some cases probably not so much, depending on how recently we did it and how well you understood it and you did it the first time. Okay. And that's, I want to gauge that so I know what I need to emphasize as we go through this 3-day review. Okay, so You know, one thing you might want to do is just you list it out off the top of your head what the properties of logs. Okay. Wouldn't be a bad thing to throw in there. And plenty of other stuff like, okay, how do you estimate a solution? From a graph. Okay. Now back to your logarithmic functions. This graph is inverse to this graph. This graph has the point 0, 1, as you well know, because x equals 0. You get 2 to the 0, which is 1. So 0, 1 is on this graph. And that means that 1, 0 has to be on this graph. So 1, 0 is a point on your basic logarithmic function. Okay? On the graph of the basic logarithmic function. The next easiest point to get here is 1, 2. 2 to the 1 equals 2. So you have the point where x equals 1, y equals 2 means you're going to have a point up here where y equals 1 and x equals 2. So these points, you just reverse the coordinates and you get this graph. So you're at no risk at all, if you know that, of drawing an incorrect graph of a log function. When I might ask you, okay, estimate the log of 3. This question could well occur on the exam, okay? Or tell me the solution to the equation 2 to the x equals 5. Okay. Now, the neat thing about these graphs is you can draw them without labeling the coordinates. So the coordinates could be anything. So either of these graphs, this is your two exponential graphs, increasing exponential, decreasing exponential, 2 to the x and 2 to the negative x, right? Okay. Depending on whether you have an increasing exponential or a decreasing exponential, you can label this graph to represent that function. It's very easy to do. Okay, we'll talk about the details, but I said you just label this thing now that you've got the graph, take that shape, label it as you wish, or as it would be labeled to represent whatever situation you're trying to represent. Okay. And same thing here. This could be relabeled to represent any log-based B function. Okay, now there's actually a log-based B of a negative, which would be this. So you could have actually do that wrong. That's a reflection. Do this. So you got a couple of log-based B functions here. Anyhow, one of these graphs can be labeled to represent a log-based B function. Okay. And we'll talk more about that because that really gives you a very broad picture of exponential and logarithmic models. All right. Now, we switch to the most recent topic, which is systems of linear equations. What do you need to know about systems of linear equations? Well, one thing is, if they're linear equations, you really want to solve them by elimination. And if I ask you to solve it by elimination, you need to know what that means, and you need to solve it that way. Because if you solve it by substitution, when I ask you to solve it by elimination, you're getting at most half credit. Okay, I respect your ability to solve these things by substitution, but you have to know what elimination means and how to use it, because that leads into what you do with augmented matrices to get solutions. and into matrix equations and so forth. Okay, so how do you solve by elimination? There are three things you can do at every step. You can multiply any equation by any non-zero number without changing its solutions. It's an equation of two variables, it has a graph that's aligned. If you take both sides of that equation and multiply by the same thing, you get the same darn line. It's the same equation. It's three equations. It's an equation in three unknowns, and you multiply both sides. Well, it gives you a plane in three-dimensional space, which is more. Some you can visualize that easier than others, and not go to complete pain with that. But multiply both sides by the same number, it doesn't change. So go back to two dimensions. If you multiply the same number and solve for the intercepts, well, your numbers on this side are just going to be that many times bigger. And the numbers on this side will be the same number of times bigger. So when you let one of your variables equal 0, you're just going to be dividing a number that's, let's say, 8 times bigger by another number that's 8 times bigger than it was, and you're going to get the same result. So multiply both equations by a non-zero number doesn't change the solutions. And it's not hard to understand that. I'm just waving my hands and talking about it, but it's not hard to understand. Okay. You can add multiples to equations and you don't change the solution to the system. Okay, I don't do that geometrically, but you can accept it just based on the idea that if this is equal to this, and this is equal to this, then this plus this has to equal this plus this. So you basically get a true statement by adding multiples to two equations. As long as you're talking about non-zero multiples, it is to be technically correct. I put the word non-zero in here. If you multiply both sides of an equation by 0, you lose all your information. You have this equation that has a graph, and all of a sudden you have 0 equals 0 and say, that's true, but that's not telling me anything. Okay? And have to be non-zero multiples here. The other thing is, you can change the order of your equations. I've said it before, I'll say it again. You have two equations with two unknowns, you get two graphs. Maybe they intersect, maybe they never intersect. And maybe they overlap, maybe they're the same. Okay, those are three possibilities. Either way, if you change the order of the equations, the graphs are still going to be the same straight lines. Once you have the graphs, you don't know which one was listed first, which one was listed second. It doesn't matter a bit. If you get this line and they intersect here, it's the same as if you get this line, then this line, they're still going to intersect in the same place because they're the same two doggone lines. Okay? So they're very easy. It's not a rule that was handed down on a stone tablet. There's a reason for it. And it comes down to that. Now, to do a formal proof of that in the general case, gets a little more involved, and we're not going to try to prove that. But with that simple example, you can accept this. Okay, so you write the equations in a more convenient order. Slug. Okay, how do you represent these things by matrices? Well, augmented matrix. I don't have anything in here except this dotted line to indicate that to the left of the dotted line, you have the coefficients of X, Y, and Z, or whatever it is. And to the right, you have the numbers to the equal of them, to the right of the equal sign. Okay? So it just kind of tells you where the equal sign is. You have a single column here. You have as many columns here as you have variables. If you have just X and Y, you're just going to have number here, a number here, number here, number here. That's one column, two columns, right? You have three variables, X, Y, and Z, then you're going to have three numbers. Here, here, here. I'll give you three columns. So when I say represent by matrices, it's maybe too much abbreviated. I mean represent a system of equations by matrices. Okay. I don't have the right system in there, but it's implicit. I mean, exactly what you expect. I didn't have the word in there, and everybody put it out right last time. Okay. So you have an augmented matrix, or you can have a matrix equation. You have the coefficients over here, you have the variables here, and you have the numbers to the right. And when you multiply this row by this column, you get the first equation. If you multiply the second row by the second column, you get the second equation. Okay, or you get the left-hand side of the second equation, which would then be equal to the second number in this column. Should be familiar. We haven't talked a whole lot about matrix equations since we did it, because that's actually pretty easy. Mainly because we're not inverting the matrices. Okay, we got hung up. And it usually happens. We got hung up on the mechanics of reducing matrices. Had to spend an extra day on reducing matrices. Hopefully everybody's in good shape on that now. If not, we can do the stuff. And when we get to the review, I'll pick up on it, and I'll, when we expand on this, we'll at least do that. The neat thing about matrix equations is you can write this matrix times this column equals the set of numbers to the right of the equal sign. You can multiply both sides by the inverse of this matrix. Just like if you're doing 5x equals 17, you multiply both sides by 1/5. They probably think you divide by 5, which is fine, but I'm just doing multiplication because you can't divide by matrix. Okay, so if you have 5x equals 17, you multiply both sides by 1/5. 1/5 of 5 is 1, that just gives you x. And 1/5 of 17 is 17/5, 3.4. Okay. You can do the same thing with matrix equations, except you can't talk about the reciprocal of a matrix. You talk about its inverse. Well, when you multiply by 1/5, you really multiply by 5 to the -1, didn't you? Because now that you understand negative exponents, at least to the point where you know that 5 to the -1 is 1 over 5 to the 1. Okay, so you multiply that 5x equals 17 by 5 to the -1 on both sides, and you get what I just said. 5 to the -1 times 5 is 5 to the 0. If you use the laws of exponents, you just use the fraction, you divide, you get 1 either way. Okay, when you multiply both sides of this equation by the inverse of the matrix, inverse times the matrix actually gives you what's called an identity matrix. It's just like analogous to 1. And when you multiply that by this, you just get this. So you multiply both sides by the inverse, you get this equals, of course, then you multiply this side by the inverse. Okay. That's convenient because if you're using machinery, I told you earlier, you go to Wolfram Alpha. Showed you how to write out the matrix and its inverse. Doesn't matter if you remember that, you're not going to be testing on it right now. But understand, it's very easy to write out the matrix equation and ask Wolfram to solve it. Especially if you just write, okay, this column vector can be semicolons in the columns, equals the inverse of the matrix times this, punch a button, it'll calculate. Give you a solution there, quicker than you can think. Okay? So it's important to understand this much about matrices. How do you multiply them? And what do you do to solve a matrix equation? Calculating the inverse matrix is, well, it just involves reducing the matrix. If you can reduce the matrix, you do it with an augmented matrix. Okay. Notationally, there are real advantages to matrix equations over augmented matrices, but either one. Either can be done by machinery. We'll learn to do this by hand. We will not learn to inverse matrix, to calculate inverse matrices by hand. That doesn't mean I wouldn't put the instructions for calculating an inverse matrix on a test. As a, you want to show off, do this, but it's not going to count against you. You can ignore it. And you probably will, because you'll be too exhausted by the time you get to the extra problems to even want to think about it. Okay, that's fine. But if you're really in the mood to show off, you think you really nailed the test and you really want to show off, you'd be able to follow those instructions. If you can reduce an augmented matrix, you can follow the instructions. I'll even tell you. You put this matrix on one side of these dots. You put the identity matrix, 1 0 0 0 1 0 0 0 1, say. On the other side, and you reduce this side, and what you get on the other side is the inverse. That's simple. It's just a pain. Okay. You could follow the instruction. If I told you to do that, put that in writing, you would be able to do it. It's a little beyond the scope of what we need to do in this course, so we're not doing it. But you're right at the point where we could. Okay. I've been running my mouth for over 35 minutes. Okay. Reduce an augmented matrix and interpret. Well, you know how to reduce an augmented matrix. Switch rows if it's convenient to do so. Multiply rows by non-zero numbers. Add multiples of rows. Just the same thing you do with the equations, except you got to be a little more organized when you put it into the form of a matrix. You sprawl your equations all over the page. If you organize reduction of the matrix in the recommended fashion, you might have stuff sprawling over here where you do some calculations. As long as you don't put them in the column, you see the whole thing. You get a 1 here, and then use that to get zeros down here. And you get a 1 here, and use that to get zeros above and below it. You get a 1 here, wipe out everything above and below it. That's a process. You don't confuse the process by putting a bunch of extraneous foolishness. It's not foolishness, it's side calculations that belong in the side. Okay? Put the side calculations aside, just watch the matrix evolve. Usually only takes 4 or 5 steps. Or two matrix, only usually about 3 or 4 steps. Okay, so you add more, you do some combination of these 3 things. And you reduce it down to this point. That's familiar to you. You more or less know how to do it. Most of you probably need a little more practice with it. But it's not difficult. You just got to get it straight and practice it enough that you know where you're going, you know what to look for, and you know what to do in each step. Okay, so nothing to that. Multiply matrices, well, that's real easy. You know how to multiply a row by a column, you get a number, right? So this just indicates a row, simple row, put some dots here. Multiplied by a column, and the column reads X, Y, Z, W. Okay, and in the real world, a lot of the matrices people work with have like 1 million rows and 1 million columns and 1 million numbers in this thing, and they don't do them by hand. Okay, wouldn't be enough time in 100 lifetimes. And you'd probably make a mistake on the first day. So your whole life's work could be done with it. Okay, machines do it real easy. And 1 million by 1 million matrix even takes a powerful machine a while. They're always trying to find ways to multiply matrices more efficiently. And they actually came across that recently. Cut out a step. And if you're doing 1 million by 1 million matrix, cutting out 1 step on each calculation makes a big difference. Kind of exponentially start to decrease the time it takes. You get the time producing matrix along the curve like this. So, having mentioned that, I expect you to research that and give me a complete report before the final. Fair enough? Because I don't understand. Actually, I do understand it for simple matrices. Okay. But I don't think I can tell you right now. I understand it. And I look at it again for 5 minutes and I can give a good explanation, which I'll probably forget the next day now. But I don't remember things I've known for 50 years. It was not past. Stuff I did yesterday. Okay, so anyhow, there it is. And there's where we're at in the review. We did that a little more quickly in class during the last hour in the support class, but also with some writing. I said, okay, fill in these, fill in these. That's what we're going to do right now. We're going to fill in some of this stuff. Okay. And if you're real good and behave yourselves, I might even tell you the general problem you're guaranteed to see on the exam. I'm going to tell you at some point. You want to see it today, behave yourselves. Okay? No, seriously. You don't have to copy all this stuff down. Don't waste your time right now copying the stuff down, unless that's the only way you can stay away from it or keep your mind what you're doing. And sometimes it is. So I'm not going to judge whether it is or not, but what I recommend you do is look at this, think about it, and just list one of these headings and give me a little more. You may be a little bit of what I just said. You're not going to remember it all. I'm trying to give you a sense and trying to get your brains working on some of the fundamental examples. The analogy I used in the last class is all this stuff is like a big puzzle. Okay. If you get the puzzle put together, you get a simple picture. You can understand. Now, it's not a perfect analogy. That's really, we want things to fall into place here in this last week and a half, so that week after next, when it could come showtime, you got at least a pretty good picture of that puzzle. There's a doggy over here. There's a sailboat over here. Okay. You're not sure where that mountain is in the middle, but you think there is one. Okay. Whatever level of completeness you can achieve in putting this all together as a puzzle is going to be real beneficial to you in the exam. You'll have a exam. You know where you are. You'll be able to penetrate further into any problem that you don't really understand. Okay. And at least get partial credit, and you'll be able to get full credit in a lot of problems. Hoping everybody gets full credit in every problem. Might be a stretch. It's not an easy course. Okay. But start putting it together. So fill in some details on some of this. Even if they're the simplest possible details you can think of, you're thinking. And you're putting together the puzzle. Even if the piece doesn't fit perfectly, you're making progress. Okay. Let me just address what I'm seeing. Most people, of course, are still working on matrices and augmented matrices, but still having some problems with this. Okay. So instead of giving you the general problem that I wanted to give you, I want to just clarify a couple of things about the process of matrix reduction, whether you're working on it or not. The majority of the class is working on matrix reduction, which tells me that the minority who chose to do something else and did it quite well, probably need to see it too. Okay. Okay, that's a nice fresh board here. Yeah, I'm going to leave these two boards there. If you want to take a picture instead of looking at this, but I recommend you review the whole development. Start with what I did last hour. Okay. So you get this whole scheme. You start to get the scheme into your head. Okay. I'm gonna write down the matrix. I'll even put a 1 here. Okay. Now, I want you to tell me, write down that matrix and circle the next number in that matrix you need to work on. You know where you're trying to get, trying to reduce it. And yet this form where the asterisks are numbers that just go along for the ride. Okay. In other words, when you do something to a row, you do it to the whole row, and that's going to change these numbers over here. Okay. But what you get is focused on the left-hand side, where you're trying to get this identity matrix. Let's call it an identity matrix. Not always possible to get an identity matrix. We're not going to worry about that right now. In this case, you will be able to get an identity matrix. Okay. So don't worry about the whole process. What's the next step? Circle the number you want to work on, and then, if you know, tell me what operation you're going to do and show me the matrix you're going to get next. Okay? But at least circle the number you want to focus on. Now, the only thing difficult in this class is getting a stupid record button to work. Okay. I don't know why it's delaying like this. Well, the thing we want to concentrate on is this number. And we want to make this number into 1. The easiest way to do that is multiply this row by 1/2. Okay. So the way I would write that is we keep our matrix all the same, but we multiply 1/2 times the second row of our previous matrix. So we get 0, 1, 3, 2, 1, 3, and 9/2. Okay. And then we don't change anything else. What do we do next? There are 2 numbers that we can change, make everything match. Okay. So what is the next number that you want to pick on? Hopefully you see that when you have a 0 in front of something where you want to have a 1, you just divide by that something, divide the whole row by that something. Okay, what's the next thing we want to do? Well, let's say next thing I want to pick on is 4. Then I want to get that to match my 0. Well, when I multiply by 1, so when I add it to 4, I get 0. Be -4, right? So I multiply, well, off to the side here, I'll write it out like this because I kind of like the way this works. I do 4 times 0, -4 times 0, 1, 3, 9/2, right? And I add that 1, 4, -2, 5. Okay. Well, I'm multiply it off and look at this. Until you know exactly what you're looking at, you can do it in your head. You're not going to be under time pressure. Except you really want to get to bed at night. You take the exam, but you can get it done by the time. That's okay, you got -0, -4, -12, negative 18. You can verify, multiply this by negative 4. You can tell whether I did it right or not. Check. And then you have 1, 4, negative 2. You add those together, you're going to get 1, 0, negative 14, negative 13. So now over here you say, okay, what I just did was I did row 1 negative, row 1 minus 4 times row 2. And it gave me 1, 0, negative 14, negative 13. I still have my row 2. I don't want to mess with this 1. I've got it where I want it. I don't want to change this row. I operate on it off to the side, not in my column. Okay. Now, show me with your fingers. What's the next number you want to operate on? I wouldn't do that one yet. What's the next number you want to change to get to this point? Okay, I've got one vote, got another vote. Let's see. Okay, yeah, one of your fingers is hiding there. I wasn't sure, but I know you're saying so. Figure that's what you have. Well, the next number to do is this one. So I get my 0 here. I don't want to operate on this negative 5 here because I don't have 0 in front of it yet. Okay. And anything I do to it, if I don't have 0 in front of it, anything I do to it to get a 0 here is going to change it. It's not going to be 1 anymore. Okay. Think about that. Well, I'm not going to do that because we're pretty much coming out. But if you understand this, you're just about home free. Then the next number you're going to want is that one. Whatever you have here after you get rid of the 3, because that's going to change these numbers. Whatever number you have here, you're going to divide by it to get a 1. Then you're going to add a multiple of it here to get 0, and multiple of it here to get 0. Same thing we just did. And you've got it. The 2 steps you have to see is look for a way to get a 1 in the right position. You get it in the wrong position, you're going to find out that it doesn't work and you won't do it anymore. Okay, so look it up. Okay, for homework, it's not going to be an open math assignment. We're done with those, but use them for review. Okay, actually there is one, and probably delay it a little bit. But go back over this in detail. Spend as much time as you can reviewing what I said, what I showed on the board, and figuring out, researching. Okay, you see exponential equations, you see what I've got there? Read your book. Okay, book is right there online, read it, and that's going to really help things fall together. Okay, and then come in ready to go a little deeper into these topics.